Hi everyone, and welcome to our last screencast on enzymes. We learned last day all about enzymes and how enzymes are involved in metabolism. And of course, if you want any reactions to happen in your body, you're going to need ATP as well. So let's refresh our memories about what metabolism really means. Metabolism is all of the reactions that happen in your body. And they're broken up into two sections. Catabolism is when enzymes help to digest or break down bigger molecules into smaller molecules. This is just another word for hydrolysis, and you need water to make that happen. Anabolism is when you need enzymes to help build molecules or form bonds between molecules, build polymers from monomers. And this, of course, is just another word for dehydration synthesis. And you lose a water every time you form a bond in the body. So when you take all of the catabolic and anabolic reactions in the body and you put them together, that, in essence, is metabolism. If you're going to do any of these reactions, you need ATP energy to do that. So what do we know about enzymes so far? We know that enzymes act as a catalyst. They're not consumed or used up in a reaction. They can be used over and over and over and over again, so you don't need very much of an enzyme to make a reaction go. And they speed up reactions, you'll remember, by lowering the energy of activation, lowering that hill so reactions don't need as much energy to start. The main thing that we're going to be learning today is the factors that can affect the rate of the reaction when we're talking about enzymes. How can the speed of a reaction be changed, be altered? How can you increase or decrease the rate of a reaction? First factor is concentration. And the amount of enzyme or the amount of substrate that you add to a reaction, if you add more of it, it will increase the reaction rate. So if you have a solution with substrate in it and you add more enzymes, the reaction rate will happen faster. If you have a solution with enzymes in it and you add more substrates, well, then the reaction will happen faster. So if you've got a really dilute solution, the reaction won't happen very quickly. If you have a very concentrated solution, the more you add, the more the reaction rate will increase. So you're going to see a graph that looks like this when we're talking about concentration. And you always want to pay attention to what's on the bottom of the graph. This graph is saying substrate concentration. So if you start out with 0 substrates and you add a little bit more, then you're going to make some products. You add more products, you add more, and the reaction rate is increasing until you reach this point. This is the point of saturation, or this is when the enzymes are completely saturated. And what does that mean? That means the enzymes are working as fast as possible. They're changing as many substrates into products as they can, and they can't work any faster. So even though you keep adding more and more and more and more and more and more substrate, you won't be getting any product any faster than you're getting it already, because the enzymes are already going as fast as they can. So what could you do to increase that reaction rate? Well, add some more enzymes. You've already got lots of substrate. You keep adding more and more substrates, not doing anything. But if you add more enzymes, then you've got more workers to keep turning more and more substrates into products. And the reaction rate will increase. Similarly, if you're looking at a very similar graph, but it says enzyme concentration on the bottom, what that means, you've got a lot of substrate already, so now you're going to add some enzyme. So you don't have any enzyme to start, so the rate of reaction is 0. Add a little bit of enzyme, the enzymes start turning the substrate into product. You add more, you get more product, the reaction rate increases and increases until you reach this point. This is not the point of saturation. This is reaction rate isn't increasing anymore, because even if you add more enzymes, you've already turned all the substrate into product, so there's no more substrate available for the enzymes to work on. So even though you keep adding more an enzyme, more and more and more and more enzymes, the substrate's all gone. It's been turned into products. But the rate of the reaction is not going to be increasing. So what can you do to increase the reaction rate in this case? You've already got tons of enzymes, so how can you make the reaction rate increase? add some more substrate. If you add more substrate, now the enzyme has something to work on to turn into products again. So always pay attention to what the bottom of the graph is saying, because your answer will be different if it's the concentration of the enzyme versus the concentration of the substrate. The second factor that can affect the reaction rate is temperature. Now, if you have a graph that looks like this, and we start at 0 degrees Celsius, it's really cold. And when it's cold, those substrates and enzymes are not going to be bumping into each other. They're not going to be colliding with each other very quickly. And if they don't collide, if they don't meet up, they're never going to be able to make products. So at 0 degrees, when it's cold, you get a very small amount of products being made. The reaction rate is very slow. But if you then start increasing the temperature, what will happen is you'll get more and more collisions between the substrates and the enzymes, and you'll get more product being made. So it'll get faster and faster and faster until you reach this point. Now if we're talking about the human body, at 37 degrees, that is when the most product will be being made, and that is because it is the optimum temperature. That's where you're going to get the very most collisions between the substrates and the enzymes. And so you get the most product made at the optimum temperature. But as you increase above 37 degrees and get closer and closer to 60 degrees Celsius, it gets very hot at 60 degrees Celsius, and you see a sharp decline in your graph because all of those enzymes are going to start to denature. And a denatured enzyme, a denatured protein, we know, loses its shape. And if the shape of the active site is no longer exactly the same as the shape of the substrate, they can't fit together and you will get no product. So things get shut down pretty quickly when it starts to get hot. So on the left side of the graph, you're still getting reactions. It's happening very slowly because it's cold, and when it gets hot, it denatures. So this is graph that you'll have to recognize. If you see a graph that looks like a slow sloping hill on one side and a steep cliff declining on the other side, you'll have to be able to recognize, oh, that's a temperature graph, and be able to explain why it's such a slow increase and a fast decline. Next factor that can affect the reaction rate is pH. If you're too acidic or too basic, again, you can denature the enzyme, change its shape, and so the enzyme can't do its job anymore. And every enzyme that works in your body has a different optimal pH that it likes to work at. So if we look at this graph, let's look at the enzyme salivary amylase. Salivary amylase is an enzyme that works in your saliva. It is neutral in your mouth, so it has an optimum pH of 7. So let's draw our graph at pH of 7. So at the optimum, the enzyme and the substrate are colliding with each other really quickly. The enzyme is doing a great job of making products as fast as it can. As you decrease the pH and you get more and more acidic, what's going to happen is you're going to make less and less and less product. And that is because the enzyme is being denatured. Positive hydrogen ions from the acid are going to mess with the negative R groups in the enzyme, and it'll take that nice, perfectly three-dimensional shape, and it will unwind it and denature that enzyme so it can't do its job anymore. If from optimum you start increasing the pH, so you're more and more basic, and there's more OH negative ions, hydroxide ions, then the enzyme will also denature on this side of the graph. And that's because the negative OH is going to mess with the positive R groups in the enzyme. And again, that nice three-dimensional shape is going to unwind and will be completely denatured, not able to do its job anymore. So this is what that graph will look like. Sloping hill on either side. It's too acidic on the left side, so it denatures. It's too basic on the right side, but denatures as well. And slightly above or below optimum is the only time that this particular enzyme is going to be able to do its job and make some products. Different enzymes like to work at different pHs. They have different optimums. The stomach has an optimum of around 2.5. The intestines have an optimum of around 8.5. And so depending on where you are in the body, that will determine how well you work at a certain pH. The vagina also has an optimum pH of 2.5. So if you take a look at pepsin and trypsin, both of these are enzymes that digest proteins. Pepsin works in the stomach, so it has an optimum around 2.5. works the best at that pH. Trypsin, on the other hand, works in your small intestines, and trypsin has a pH optimum of around 8.5. And again, they're both working on exactly the same type of substrate, on proteins, work at different optimum pHs. Inhibitors is another thing that can affect or interfere with how an enzyme is able to do its job. There's two types of inhibitors, competitive inhibitors and non-competitive inhibitors. We'll talk about both. A competitive inhibitor is one that will compete with a substrate for the active site of an enzyme. And so competitive inhibitors are usually very similar in shape to a substrate. So they'll jam themselves into the active site of an enzyme and prevent the substrate from being able to join the active site of the enzyme. And so you're not going to get any product forming from enzymes that have inhibitors stuck inside their active sites. Here's the inhibitor. It's preventing the substrate, even though it can try again, that substrate's not going to be able to fit into the active site. And you won't get any product forming from that enzyme. That enzyme can't do its job. These inhibitors can be removed though, so that's good news. So the enzymes can become active again when the inhibitor is removed. So you see here in this picture, the competitive inhibitor is sitting inside, taking up the space of the active site, so the substrate can't fit there. So in this case, you'll get less product being made. We see this would be normal when there's no inhibitor, just a normal reaction rate. And when you have an inhibitor, the reaction rate is going to decrease slightly. You'll get a little bit less product because some of those enzymes have been attached to inhibitors, and so those enzymes won't be making products. An example of that is pesticides. This is how we use pesticides to mess with bugs and kill them. The second type of inhibitor is called a non-competitive inhibitor, or an allosteric inhibitor, and that's because it attaches in the allosteric site of the enzyme. And what it does is it somehow changes the shape of the enzyme, so the active site is no longer the right shape. So again, the substrate can't join and no product will be made. So it denatures the enzyme by jamming itself into the allosteric site and changing the shape of the enzyme. And lots of times this can be permanent. So non-competitive inhibitors are more dangerous than competitive inhibitors. And if they're permanent, this can make you really sick because your enzymes can't do their job. An example of that is lead and mercury. Lead and mercury are both heavy metals, and if they get into your nervous system, they can make you really sick. They can give you lead poisoning or mercury poisoning because they are messing with the enzymes in your nervous system that would normally do specific jobs for you. So here's an allosteric or a non-competitive inhibitor. You see when it joins the allosteric site, the shape of the active site changes, so the substrate can't fit anymore. Here it is again, and no product will form from that. So if you looked at that graph, you'll get much less product being formed. And if you compared the two graphs, competitive and non-competitive inhibition, you'll see that you get a little bit less product with competitive inhibitors and a lot less product with non-competitive inhibitors. Non-competitive inhibition is not always bad, because this is how we do homeostasis in our bodies. This is how a negative feedback cycle works. So if you look at a metabolic pathway where one product is turned by a second enzyme into another one, and there's like 5 or more enzymes involved, sometimes when there's too much end product being made, or when your body has enough of that end product will go back to one of the enzymes and it will deactivate it. It will change the active site of the enzyme, and then you won't get any more product being formed. So essentially, product will go back and shut itself off. This isn't permanent, because when your body realizes it doesn't have enough of that product anymore, then it will turn on again. So this is just temporary. It temporarily attaches to the allosteric site, and the enzyme is temporarily denatured, but when your body needs more of the product again, that will be removed from the enzyme so the enzyme can start doing its job again.